Before I answer the question I posed at the end of the last clip, I'll just comment that this reference point moving around the circle has a velocity tangent to the circle, and that velocity is just equal to the angular velocity omega multiplied by the radius of the circle, or whatever quantity represents the radius of the circle. If the quantity representing the radius of the circle is just a displacement, then v of t is going to be a velocity. It's going to be tangent to the circle, and the scale of v of t has nothing to do with the scale of r of t or with the scale of a of t. A of t being just the centripetal acceleration vector of this point moving around the circle. If we project the v of t vector onto the x-axis, we get a vector that represents the velocity of this particle moving according to this equation. In other words, this vector, as we move around the circle, is going to get shorter and shorter till we get to this point. Then it's going to get longer and longer till we get out to here. Then it's going to get shorter and shorter as we move around here. Get my arm in the way. And then it's going to get longer and longer as we move around to here. Then it's going to start getting shorter again. This v of t vector is going to be constant in magnitude as we go around the circle. But when we're here, the v of t vector is going to be perpendicular to the x-axis, so that its projection on the x-axis is going to be 0. When we get to here, then v of t has grown to some size, and when we get to here, v of t will be, the velocity down here will be as big as the velocity, the vector velocity out here. The acceleration, similarly, will have a projection that varies in length as we change position around the curve. That's basically a picture of simple harmonic motion. There's more to it, and we see that there are a lot of calculations and stuff around here, and we'll get to all that, all those details. But right now, let's just see that there's this reference circle that gives us a really good and fairly complete model of simple harmonic motion, at least as far as the position, changing position of an oscillator, the velocity of that oscillator, and its acceleration. And I'm actually a small step ahead of myself talking about simple harmonic motion because we haven't really said that yet. But since I let the cat out of the bag, simple harmonic motion is just what you have anytime you have a linear restoring force of the form F net equals negative kx, which is, of course, the premise that we started out with at the beginning.